All right, so we are studying fluid dynamics. Here's a picture of smoke, and as you all correctly pointed out, smoke is rising. But why is it rising is the question. Okay, so presumably this is a cigarette smoke. Okay, that air got warm next to this lit cigarette, and when it got hotter, it expanded, and the density decreased because the volume increased. So the density of this air is less than the density of the surrounding air. Okay, and you learned that if you have an object whose density is less than the density of the fluid and it's immersed in, it will float. So it will keep rising up. Okay, so it feels a buoyant force that is greater than its weight, and it starts accelerating upward. How long will it accelerate upward? So as long as it's warmer than the surrounding air. Okay? So this air keeps rising. It keeps accelerating. When it keeps accelerating, what happens to the velocity, to its velocity?
It increases.
So velocity increases linearly with time. Okay. So here's the deal. Okay. So as this packet of smoke is rising, it's going faster and faster. And you see, after it reaches a certain critical speed, now it's become turbulent. This flow is turbulent. What's the difference between this flow and this flow? Do you guys see anything?
All the particles are moving in the same direction, one's linear, and then it becomes turbulent.
Okay, so here's the difference. If your neighbor's here, when the flow is laminar, you'll still be neighbors. Your neighbor's here, oops, I should actually. So your neighbor's here, you'll be neighbors there. But you get into turbulent flow, and all bets are off. Okay, so small changes. So when you learn differential equations, you'll learn small changes in initial conditions can give you drastically different outcomes. This flow has become chaotic. Okay, so if your speed is greater than a critical speed, the fluid flow becomes chaotic. Okay, so why do we care about this? So for instance, this is blood flowing in your blood vessels. Okay, if the blood flow becomes turbulent, there's more friction. Your heart has to work harder to pump the same, to maintain a flow rate. If you're pumping oil in a pipeline, if you're pumping water to the city, you don't want turbulent flow in your pipelines. If you have turbulent flow, what happens? Your electric bill is higher. Okay, you have to pump harder. If there's turbulent flow in your blood vessels, your heart has to work harder. Okay. All right, so the motion of real fluids is very complicated and not fully understood. So we'll discuss the flow of ideal fluids. Ideal fluids are fluids without friction, viscosity is 0. Okay, that's one of the things we'll consider. Okay, fluids in motion transition from steady laminar flow to turbulent flow above a critical speed. Okay, so in turbulent flow, there's greater friction, it's harder to pump it, okay, and so on. Pressure and velocities are unpredictable, and so on. Okay, so if the critical speed, this speed is characterized by something called a Reynolds number. Okay. Now here's a pretty powerful statement. Yeah, so Heisenberg was one of the founders of quantum mechanics. He was a contemporary of Einstein, of the same stature. And here's a statement attributed to him. Werner Heisenberg once said, given the opportunity, when I meet God, I'm going to ask him 2 questions. Why relativity and why turbulence? I really believe he'll have an answer for the first. So what he's saying is nobody understands turbulence. Okay. Yeah. So everything we learn now in the second half of the chapter will apply here. You rise 10 centimeters and we don't know how to describe that. Okay? All right. Turbulence is characterized by chaotic changes in pressure and fluid velocity. Okay? So when does turbulence sets above a critical speed? Resistance increases with a corresponding drop in flow rate. So for instance here, okay, so here is a blood vessel, and if you have plaque deposit, you learn that the narrower the fluid, the faster it'll move, and this can get turbulent. Okay, so in a non-ideal fluid, you have to maintain a pressure difference, higher pressure, lower pressure, to keep a fluid moving. Okay, so what this is telling you is the flow rate. Yeah. So to maintain a given flow rate in turbulent flow, you have to work harder. You have to maintain a higher pressure difference. Okay? So if your heart is working harder, you're spending more energy on that. Okay, so turbulent flow can occur in large arteries at branch points, in diseased and narrowed arteries, and across stenotic heart valves. Okay, again, so the flow rate decreases in turbulent flow for a given pressure. If the flow is laminar, you would get a flow rate that high. Okay? And your pumping bill, electricity bill, will be smaller. Okay? Viscosity is friction in a fluid. Okay. What does friction do? Friction converts kinetic energy, mechanical energy, to heat. Okay, so if there's viscosity in a fluid, a moving fluid, layer of fluid would slow down. What happened to that kinetic energy? It got converted to heat. Okay, so that's what viscosity would do. So if the viscosity was 0, all you have to do is get water moving in a pipe, and then it will move forever. Okay? And you wouldn't have to pump it. Okay? So, well, at the same level. Okay, so viscosity causes part of the kinetic energy of a fluid to be converted to internal energy. Okay, so again, we will consider ideal fluids. Ideal fluids are non-viscous. We'll consider situations where the flow is steady. Okay, so everything we say won't apply to this situation. Here, you can stand at a location and measure the velocity, and it's constantly changing. So that's not steady flow. You can stand here and measure the velocity, and the velocity will be constant. Okay, as a function of time. You can stand at a flowing river, a steady flowing river. You can measure the velocity at any location, and that velocity will be constant with time. Okay? So that's what we're considering. We're considering situations like this, not stuff like this. Okay. So flow is steady, flow is non-viscous, fluid is incompressible. Okay. Now water is essentially incompressible, but we'll apply this to air as well. Okay. So gases as well, but gases are compressible. But the situations we apply it in, they don't undergo too much compression, so we'll apply there. And here's the last condition. It is irrotational. Irrotational just means there are no eddies. Okay, so if you put a paddle, so here's a steady flowing river, you can put a small paddle anywhere, and the paddle won't spin. Okay, that's what we want. So what we want is the velocity on this side of the paddle, and this side of the paddle is the same. Okay? But in an eddy, you'll have the paddle would spin, okay, a little fan would spin. So the flow is irrotational. Right, so the first equation we'll look at is the equation of continuity. So here's a pipe whose width is changing. All right, so let's say, again, we're considering incompressible fluids. Let's say 5 gallons a minute are flowing into the pipe here. If there are no leaks, how much water is flowing out? 5 gallons a minute, okay, no matter what the shape of the pipe. Okay, so the flow rate has to equal, and the flow rate is equal to the area of cross section times the velocity, okay? So this is constant everywhere. Okay, so if the area increases, if the width of the pipe increases, the velocity has to decrease. Okay. All right, so let me show this to you. Okay, so what I'll do is, I'm sorry? Okay. So speed, I'll measure the speed here. So you see the speed is 1.6 meters per second, and the width increased, and the speed decreased. Okay. All right, so this is the equation of continuity, okay? Oh, man. All right,
So the V in that formula is for velocity and not for volume?
I'm sorry?
In that formula, that is the V stand for velocity or?
Yeah, V stands for velocity. A is the area of cross-section of the pipe. Now, so Mr. Bernoulli studied the following. So he studied pipes whose elevation was changing and whose cross-section was changing and so on. Okay. And, you know, what you find is as the cross-section changes, you see that the velocity changes at every location because the flow rate is constant, and so the velocity, the wider the pipe gets, the flow rate decreases. Another thing that must happen is, so if I toss this keychain up, what happens as the keychain rises? The speed changes with height. So just like that, the water, its speed decreases with height. Okay. So what Mr. Bernoulli studied how does the pressure, speed, and all that change. Okay. And he just applied conservation of energy principles. Okay. So for an ideal fluid flow, okay, when we say ideal fluid flow, what is it? It's a frictionless fluid. Viscosity is 0. Okay. For an ideal fluid flow using conservation of energy principle, Mr. Bernoulli showed that the pressure at any location plus the kinetic energy per unit volume, so you can take any location, the pressure plus kinetic energy per unit volume plus the potential energy per unit volume, the sum of these three terms is constant. Okay. So the sum of those three terms at this location and that location are the same. Okay. That's what Mr. Bernoulli showed. Yep. I'm sorry? So this, we'll use this in conjunction with this. Okay. This tells you how the velocity changes with the cross section. Okay. So as long as you're maintaining flow rate, you have to satisfy this equation and this equation. All right. Now you want to remember this. We'll use this all the time. Okay. So this is Bernoulli's equation. Again, what does this say? The pressure at a given location plus the kinetic energy per unit volume plus the potential energy per unit volume. The sum of those three terms is constant, okay, for a fluid. All right, so now let's apply that. You guys might have experienced this. So, again, so what is this? We'll write down Bernoulli's equation P1 plus 1 half rho V1 square plus rho GY1 is constant. Okay. So when you drive next to a truck, okay, what happens is the air here between the truck and you guys flows faster than here. Okay. So let's say this is 0.1, this is 0.2. Yep. P2 plus 1 half rho V2 square plus rho GY2. Yeah. That's equal to that. Let's say this is 0.1, this is 0.2. These two terms are the same, so they'll cancel. Okay. This velocity is smaller, so this pressure has to be greater. The velocity is smaller, pressure is greater. Velocity is greater, pressure is smaller. So this is what I want you to remember for the rest of your life. The faster a fluid is flowing, the lower the pressure at that point. Okay? All right, so what happens? The pressure is greater here, the fluid is flowing slower. The pressure is higher here because the fluid is flowing faster. And so you feel this push towards that truck. Okay? I don't know if you guys have experienced this, but try and notice that. So again, so the faster a fluid is flowing, the smaller the pressure, the lower the pressure. Okay? And that's what planes use. So here's a plane flying in that direction. So air is flowing over the wings. And all you have to do is shape this airfoil such that this air is flowing faster than this air. Since this air is flowing faster, the pressure here is lower than here. Okay? So the pressure is lower, the pressure is higher here. Yep. And the lift, force of lift is pressure difference times the area of the wing. All right, now you might have noticed something about planes flying. Okay. So when a plane comes into land, it's flying slower, and the velocity difference is less, so the pressure difference is less as the plane comes into land. So why isn't the plane falling off the sky? This becomes smaller, and you need the same lift. How much lift do you need? The lift should be equal to the weight of the plane. So how do they deal with that? So the pressure difference is becoming smaller, so you have to increase the area of the wing. And that's what they do. They extend flaps when they're coming in for landing, okay? Because the pressure difference is decreasing. Okay, again, the greater the velocity of the fluid, the lower the pressure, okay? So this simulation just illustrates the fact that the air above is moving faster than this air below, okay? Pressure difference because of the speed difference accounts for most of the lift, you know? So you guys might know this. If the angle of attack is too steep, the flow becomes turbulent, and this increases drag and decreases lift. Okay, so you don't want to stall your plane. Okay, when you stall your plane, what has happened is flow has become turbulent. All right, any of you guys play tennis? Okay. You play tennis? So do you do top spin? Do you hit a top spin?
I just hit the ball with the bat.
Yep, all right. Yeah, so in tennis, you probably all hit with topspin. And here's why you hit with topspin. So the tennis ball is going in this direction, okay? And you can see that the ball is spinning like that. The air is flowing like this. So when you spin the ball like that, when the ball spins like this, it grabs this air flowing. Its velocity gets, this velocity of the ball sort of gets added. This air is flowing faster, and this air is flowing slower. What did we just learn? If the fluid is flowing faster, the pressure is lower here. So the pressure here is low. Pressure is low, pressure is high here. Okay? So there's a net force on the ball downward. So if you put a top spin on the ball, this ball will land inside the foul line. If you don't have top spin, you're more likely for the ball to fall outside. Okay, so this gives you more room for error, and the more top spin you put, the more inside it'll fall. Okay. All right, so here's a. If you guys haven't seen this, you gotta see this. Yep. Is that showing up? No. What's that? All right.
Our don'ts mean high quality and savings, it's true. Because everything we don't do is for you. It's an Aldi thing.
We're here at the Gordon Dam, and what we're going to do is demonstrate from the very top the effect of spin on a ball. So we're going to get a basketball and drop it from 140 metres up, one without spin and one with spin, and see what happens. Yes, it's crazy, just dropping it with no spin or anything like that. And as you could see, the ball was sort of doing the swathing, so it wasn't going directly straight. It was pretty hard to predict where it's falling. So that's really cool. Whoa, look at that go! This is very just threw it. I literally just dropped it with a bit of spin, like I didn't even throw it, and it just took off. Like we had no idea that was going to do that. But yes, so that was a pretty.
All right. So what was happening as you spun it like this? Air is flowing up from the bottom. Okay. The spin of the ball adds velocity, so this air is flowing faster than this air. Whenever fluid flows faster, the pressure drops. So the pressure on this side of the ball is less than this side of the ball, and that's what's pushing it there. Okay. So, you guys probably understand this. So, again, so let's take a basketball, like the guy did, and a tennis ball of equal size, a fuzzy tennis ball. Give the same spin. What do you think will happen? Weight, everything else is the same. Which one will go further? I'm sorry? The fuzzy tennis ball. It's grabbing the air more, okay? Making it go faster. Anyway. All right, so that's the Magnus effect, okay? So we use this principle everywhere, okay? Again, fluid moving faster lowers the pressure, okay? So, and by the way, do you guys know how does a straw work? So here's a liquid, here's a straw. Okay, Right now, what is the pressure here in the liquid? 1 atmosphere. What is the pressure here? 1 atmosphere. Okay, and that's why the liquid is not rising. So how do you make the liquid to rise? I'm sorry? Yes, so you have to decrease the pressure here. And how do you decrease the pressure? Well, you attach a person to it, and the person, their lungs expand, and the pressure here decreases. Okay. How much, if you want to drink the fluid, how much do you have to decrease by? So by the weight of this liquid. So the pressure of this liquid plus plus the pressure of the atmosphere, decreased atmosphere is equal to that pressure, and that liquid will rise. Okay. So same thing here. If you take this atomizer, if you blow on it, and you can do this with a straw or whatever, air flows fast here, the pressure decreases, and this atmospheric pressure will push the liquid up. And that liquid gets caught there and gets squirted. Okay? That's how all those sprayer bottles work. Okay? So you just have to, so again, fast-moving fluid decreases the pressure there. Okay, viscosity is friction in the fluid. Okay, and here's how you can measure it. So here's how you measure it. So if you want to measure the viscosity in this liquid, you put it between two plates. This plate is stationary, and you have to, what you do is you find the force that you have to apply to this plate to move it at constant velocity. Okay, and so the viscosity, eta is the viscosity, so the force is equal to eta times velocity at which it's moving, the plate is moving, divided by the area, times the area of the plate, divided by the distance between the plates. So if this were honey, you would need a greater force than if it were water. Okay, everything else being the same. So for honey, eta is greater. Okay? Viscosity is greater. So this is, so Poiseuille's law tells you this is the flow rate. It tells you the pressure difference you have to maintain to get a certain flow rate. So greater the viscosity, greater the pressure difference you have to maintain for a given flow rate. Okay, so for instance, I guess if you have a high blood sugar or whatever, if you're diabetic, this would be higher. Your heart has to work harder to pump to maintain a certain flow rate. Okay. And in the healthcare industry, this is very important. See, this is the flow rate, and the flow rate is dependent on the fourth power of the radius of the blood vessel. So if this were a blood vessel, and let's say you have plaque deposit, okay, if the radius decreases by 10%, okay, 0.1, okay, so if the radius decreases by 10%, so now it's become 0.9, 0.9 to the power 4 is 0.9 to the power 4 is 0.65. Now the flow rate has decreased to 65%. So the radius decreased by to 0.9 R. The flow rate decreases to 0.65 times the flow rate. Okay. So if you want to maintain that flow rate, your pressure difference, the heart would have to work 35% harder. Okay. You guys might have heard this. So in Alaska, there's an oil pipeline that comes from the Noah Purdue Bay to Fairbanks or whatever. And so what they do is in the winter, to pump the oil, they heat the pipe. When they heat the pipe, the warm oil has less viscosity, has a smaller viscosity, so you don't have to work as hard to maintain a flow rate. Okay. Because the higher the pressure difference you have to maintain, the more energy you're spending pumping the oil. Okay. So So that's why they warm the pipes. Okay. All right, guys. So that ends the lecture.